Good morning, everyone. Today, Ali is going to talk about sandboxes. Enjoy.
Thank you very much. Hello, everyone. Just a second, please. I'm Ali Polatel. Welcome to my talk on SID and an advanced introduction to secure application sandboxing. Let's start a bit of who I am, how it all started. I'm an Exarbo Linux developer. I started free software around 20 years ago with Gentoo, and I'm thankful to the Gentoo Sunrise project. I'm the main author of SIDbox, and I'm also a chess trainer and the co-founder of Chess Without Boundaries, where we try to provide accessible materials to chess players with disabilities. And last time I was here in Serbia was actually for the FIDE Olympiad for Disabilities. So chess brings us together, hacking also brings us together. So I want to thank you, the organizers, for inviting me here. So you can see here my interests and email if you want to contact me. And I'm looking for a job in case you're interested. And here is the talk outline. We'll start a bit of history, then I will explain you what our threat model is so you can actually understand what is this to be a security boundary. Then I will go into features and hardenings. Then we have a design slide. I'm not sure if the time will be enough, but otherwise we'll continue with demo and Q&A. So, history, right? And in the beginning, there was Gentoo Sandbox. Gentoo Sandbox is written in C, and it's based on LD preload. If you don't know what LD preload is, it's a mechanism to hook into C libraries calls, and it can be bypassed by running system calls yourself or running static binaries. And SIDbox 1 had this idea to overcome this difficulty, so it was based on ptrace, and it is still the default on Exarbo since 2008. And over time, Linux has gained a lot of new infrastructure APIs to do sandboxing, like seccomp, landlock, MDV, and so on. So at some point, I decided to rewrite SIDbox from scratch to make it actually a security boundary. And this is how SIDbox 3 is born. We call it SID because it's easier to slot the binaries, and it's based on seccomp unotify and optional EP trace. And the threat model, now this is the important part because we need to draw the line somewhere. And we take seccomp's threat model. We adhere to that mostly. So in this model, Linux kernel and SID binary are trusted, and anything running under it is untrusted. This means all sandbox apps. And we assume they have the ability to execute arbitrary code. And our goal is to restrict system call surface, to mediate file system and network, and to provide violation logs for this violation so the user can quickly adapt their profile for their needs. And in this scenario, external network and physical attacks are also out of scope. I mean, there is nothing SID can do if someone plugs a malicious USB stick or something like that, or if your kernel is rootkitted, again, there is nothing SID can do about this. So let's go into a bit of features which are relevant in terms of the threat model. SIDbox is unprivileged. This is very important. There is no feature in SID that requires extra privileges. This means no setuid, no eBPF, no Linux kernel modules or nothing. And SID is multi-layered. You can think of SIDbox as an onion of different sandboxes, and an incomplete list of technologies we use are seccomp, ptrace, landlock, and memory deny write execute. I will delve into them a bit more later. And SID is a general purpose sandbox. It's really hard to write a sandbox that fits everyone's case, but what we do is we make the options secure by default, and we provide a toggle for each hardening. So if some hardening doesn't work for you for some reason, you can just disable that and get the whole package, the rest of the package. And there is, we have dynamic configuration. You can configure the sandbox while it's running from within or from outside. And by default, this is not possible. You configure it when the lock defaults to on, which means after command line parsing and the configuration parsing, the sandbox policy is made immutable with the MCL system call. So even if SID wants it, it cannot edit it anymore. And lock off is just the opposite of this, when all processes inside the sandbox can configure the sandbox. This way you can make an open BSD pledge like step-by-step confinement, and in the end you lock the sandbox and there is no way return. Lock-exec is a bit of both worlds, where only the initial thread can configure the sandbox. We use use this in Exerbo for sandboxing with eSandbox helper. And IPC is a new mode. I will show this in the demo in a little bit. And this is how you configure Sandbox through a Unix socket from outside. And features, let's start with features. Of course, our prime feature is pet sandboxing, and we do pet sandboxing like AppArmor does, not like a C Linux does. So you match on pets, not labels or inodes, right? And we have refined categories, read, write, exec, IOCTL, start, read, chdir, and so on. There is close to 20 categories, and you can do sandboxing for each of them. And to make it much easier, we provide category sets like OpenBSD pledge, like read pet, write pet, create pet, and so on. And another nice thing about writing profiles with Sandbox is that we have this semantics of last matching rule wins, and this makes it really easy to write profiles. Here you see some examples. Here we use the OpenBSD pledge RPAT, which stands for start, read, chdir, and reader. And in the middle there is I can demonstrate how last matching rule wins policy works. These two rules that disallow all that files except history, this part, they both match the history, but because the last matching rule is allowed, the history is going to be allowed, but not the rest of the dot files. So this is taken from the user profile. And pet hiding is a similar feature, and this is a new feature in Sandbox 3, and we have a full implementation which covers directory listings and pet traversals, and this is hard to get right, and OpenBSD's unveil system call is also known to have problems in the history. I think they have fixed it already, but and here you see an example of pet hiding, and I start the sandbox with boot hidden, as you can see there, and when we list the rootfs, boot is not visible. You cannot cd into it. It will give no such folder directory. And again, with lockexec, we can configure the sandbox in the process, and then when we unhide boot with stat categories for pet hiding, and then everything is visible again. Pet masking is a similar to pet hiding. Here you don't hide pets, but you change their contents on the fly. You can replace files and directories on the fly, and this is like bind mouse, but it's unprivileged. So, and here I gave a very basic example where we fooled the process into thinking there is more CPUs on the server than there actually are. You can do other things with that. You can also mask directories to mask information leaks and so on. And the next prime feature of Sandbox is network sandboxing. And with network sandboxing, you can write rules based on address and port. Address can be IPv4, IPv6, or Unix sockets, doesn't matter. We support all of them. And here in the excerpt, you see, I took this from the Paludis profile. Paludis is the package manager of Exerbo Linux distribution, and the Paludis profile is the one we use with Sandbox with Paludis, right? And here you see in these 6 rules, we establish a multi-layered, two-layered firewall, two-layer sandbox. And the first 2 rules allows bind to ephemeral port and to unprivileged ports, and this is the landlock version. This is the landlock version of the same thing. Landlock has networking support with ABI4, but with landlock you cannot specify addresses. You can only specify ports. And in the middle we have this allow safe bind rule, which saves us a lot of the application, which states that every successful bind inside the sandbox is allowed listed for connect. So this especially helps when it's binding to an ephemeral port and you don't know in advance what the port is going to be. And we have in general a very flexible configuration interface with rsync like globs, CIDRs for address matching and IOCTLs. And we also have learning mode, which you can use. And there is a utility called Pandora that can automatically build profiles for you. And here I included a simple, except from a Pandora generated Firefox profile. And you can see it's trying to access my graphic card, and the IOCTL requests are easily visible. Most of them start with DRM, which stands for Direct Rendering Manager, so it's 3D acceleration. And Landlock has recently joined the party. Landlock is a Linux security module that provides unprivileged sandboxing. And in SID, there are multiple ways to use landlock. One way is to use it with SID, in which case you get it as an extra layer. We also provide you the SID lock CLI to build lightweight sandboxes, which just uses landlock on its own. And we support landlock API up to version 7, which is the most recent one. And here I included the help output of SID lock command, which gives you a full interface to interact with landlock. And the memory deny write execute is similarly a different layer with landlock, like landlock. It's most commonly known as write XOR X. The idea is to deny writable and executable memory at the same time, thereby mitigating arbitrary code injection, right? And we do this with the PRCTL, PRSet memory deny write execute, and it has some bypasses, known bypasses, and we try to harden this boundary with seccomp to stop those bypasses. An example is read implies exact personality flag, and this allows you to mark readable regions as executable, so this bypasses. And also Linux allows you to read map writable files, and then you can write it into this file, and this readable memory region is going to be updated, so it's again a bypass. You can see the Linux and hardened BSD bug reports I opened about this bypass, and we close this bypasses with seccomp. And again, we give you a CLI, SID MDVE, to build lightweight sandboxes just using this feature. You can also combine it with SID lock very easily, just combine them in the command line one after another when you are running a command. So you can have a two-layered lightweight sandbox as well this way. Another feature that's new in Sandbox 3 is encryption, transparent encryption. And this is done with this. The algorithm we use is IS counter mode and HMAC SHA-256, and there is almost no crypto code in Sandbox. There is only network code that interacts with algorithm sockets and the Linux kernel. This gives you one better performance because Linux kernel usually have optimized implementations of AES and so on. It also gives you data privacy because if Sandbox process is somehow compromised, the process itself cannot access plain text as well. And the encryption is transparent and concurrent using Linux open file description logs, and this has been included in POSIX 2024, so most file systems support it by now. A notable exception is NFS, and you cannot use encrypted files on NFS. And here I gave a basic example on how we use it. It's very simple. We provide a SIDK utility to generate a random key, and then here I start the sandbox with and configuring it such that only files with crypt extension is going to be encrypted. And when you are inside the sandbox, it just looks normal. You can write to the file, you can read the file, and there is nothing wrong. But when you exit the sandbox, you actually see that the file is encrypted. And I have actually submitted this patch to the file program. It's going to be released with the next version, so it can recognize SID encrypted files. And a bit more on encryption. We do encryption with zero copy with splice and pipes. This means there is no read and write call that reads the plain text into its address space. If you S-trace SID during an encryption, you will only see splice and pipe requests. You will not see the plain text. And another important part is we do HMAC authentication on the encrypted data. So if it's slightly modified through bit flip attacks or such, you will notice it. And here I give a basic example. SID AES is a utility to just decrypt the AES streams, and we encrypt when we decrypt the file, we just encrypt it. We see the normal content, and I here perform a very basic bit flip attack to flip just the right bit, so the meaning of life appears to be 62 right now. When you decrypt it without authentication. But when SID performs authentication, it will actually notice this is a bad message, right? And I'll go through some of our other features. These were the main and new ones that I haven't talked about previously. We have forced sandboxing to verify checksums at exec and mmap boundary. This means you can check verification for libraries and binaries all the same. I will display this in a bit. We have memory and PID sandboxing as simple and unprivileged alternatives to C groups. Again, C groups is better to use, of course, but C groups sometimes comes with privilege problems, so when you don't have it, you have these. Proxy sandboxing is one of my favorites. Here what we do is we put the process into a network namespace, we bring up the loopback interface, bind a port there, and send this port outside the network namespace to a process called sitTor. And this sitTor process does the forwarding. So you are using Tor. There can be DNS leaks, there can be other side channels, but this completely prevents, because everything is a network namespace with a single exit out, right? And PTY sandboxing is similar. We do what we do to network for terminals, and this time terminal is inside the pseudo terminal, and there is a process doing the forwarding, and this means attacks like terminal command injection with this IOCTL and so on are prevented as well. Safe set ID is when you are running daemons. I will show in a bit with Nginx. Where you safely change user and group through predefined transition rules, and you also make SID drop the user or group with the sandbox process at the same time. So there is at no time SID is higher privilege than the sandbox process. They're always on the same privilege level, right? And ghost mode is a bit of a fancy mode. People who know seccomp level 1 will understand. This is where you do where you can detach SID from the sandbox process. So what you do is you open your files, you open your connections, and then you enter ghost mode, and you only have your resources you have right now. You cannot open anything new anymore, so you can have a very confined sandbox this way. All right, so we have hardenings. I have listed the main ones here. You can find more in SID7 manual page if you are interested. First of all, SIDbox is an analysis-friendly sandbox. We have two prime features to make malware analysis easier. One is making ptrace a no operation, so malware that's trying to detect a ptracer by a failing ptrace request is not going to succeed. And we prevent process name changes with a success return. So from the perspective of the malware, it has changed its name to something like a system daemon or a kernel thread, so you cannot figure it out. But we do not change it actually. No name change happens, and we can log this as well. And one final feature we added to help in malware analysis is most malware tries to detect if they are running in a sandbox by reading the file proc/self status. And we zero tracer pit seccomp and other critical fields in this file so that malware, again, cannot detect that it's in a sandbox. And if you are a malware analyst working on Linux malware, we'll very much want to hear your feedback and can add more features as we go. And we have exec and memory hardenings. I talked a bit about write-ex or exit before. We have in addition PI enforcement. PI stands for position independent executables, and it helps with address space layout randomization, which helps with raising the bar for exploitation, because figuring out the places in memory gets much more harder because every exec is randomized, right? And we also enforce a non-executable stack. This is a bit old now. No one uses non-exec stack anymore, but it doesn't hurt to enforce it. And we have secure execution mode with AT-secure. AT-secure is a bit in the alpha auxiliary vector that the Linux kernel sets when you are executing a binary. We intervene and change this, flip this bit, so libc executes in secure execution mode. It will not load LD preload, LD library path, or other things, and do other. There are other implications of secure execution mode you can look up in the man page. And then we have SecBguard and trusted path execution, which we have inherited from GR security and hardened PST, thankfully. These are for safe execution with crash throttling. SecBguard, I'm going to display to you in a bit how it throttles crashes. Trusted path execution is to prevent you from executing files in world writable sticky directories and such, or symlinks in those directories can be used for various attack vectors, and this prevents that. We also have guards for return-oriented programming and SIG return-oriented programming, which I will again display in a bit by actually attacking an Nginx server. Then we have proc and devices hardening. when you list proc as a sandbox process, you will only see your own PID. You can only follow the magic links of your own process and so on. This prevents a lot of container breaks. And under SID, you cannot list block devices. You cannot open block devices. You cannot send IOTLs to them. So it doesn't provide a way to bypass pet sandboxing by directly accessing the block device, right? And we have, again, we confine signals and IPC, so sandbox process cannot send signals outside or so on, cannot interfere with IPC. Yeah, so, and, well, okay, I was first. Here is the design. This is a bit of a scary one, but I decided as much as I can to make it easy to understand, so bear with me just a bit. So on the top left, you see the confinement, seccomp, unotify, ptrace, landlock, and so on. And when SID starts the process, it will execute the main process, right? And then this process is going to set up the policy and then spawn a monitor process and also spawn the sandbox process. And monitor process is in return starts spawning emulator processes. There can be more than one emulator process because each one is responsible for handling a single call. So there can be more syscalls. We don't want them to block. And to fix the interruption problem, we have an interrupt thread that periodically leads from proc and interrupts syscalls, right? And IPC, which I'm going to again display in a bit, is where you connect to an IPC socket and edit the policy again. AES is for encryption, and the SID Tor and SID PTY processes run outside SID. They confine themselves on their own. And that's how PTY sandboxing and network sandboxing works. And now it's demo time. So let's sacrifice a knight on f7 for demo gods. And just give me a small minute. All right. Here you see an Nginx server running under SID. This is very basic. It's only serving static files, but I also added the endpoint, a dynamic endpoint for this. And we see here, I will explain in a bit what this is about. Someone is trying to attack and that IP is blacklisted in some list. But you can ignore that for now. The very basic thing here is that you execute SID with a profile, right? And let's look how this looks in HTOP. Here we have, ignore the sudo and vims. We have SID processes, all the threads that I explained earlier, and you see all of them are running as the Nginx user, except the Nginx master process is running as root. But this is also not really root, because this process is under SIDbox. If this root tries to create a file, the emu process with the Nginx user is going to create the file. So it will be Nginx, not root. So this is also another way of privilege drop. Let's take a look at the profile I wrote. So this is how you make the transition from root to Nginx. You can ignore the TTY profile. I included that so exploitation a bit later becomes easier. This is how you enable landlock. And here you see again multiple layered sandboxing where we allow HTTP and HTTPC ports, one for landlock and one for seccomp, right? And everywhere you will see the second two layers, yeah? When you see a lock and the without lock. See here again, this is landlock paths do not use globs. They use absolute paths you have to use with them, but with seccomp you can use globbing. Let's go a bit further. These are very, very normal stuff, like allow access to SSL certificates, so allow access to systemd journal, and then allow access to Nginx directories, run directory, log directory, so on. And system paths, these are boring, nothing fancy. Let me go a bit down. So here is how you just saw the IP denial. This is how you can make a application level firewall with SIDbox. These are, let me show you one of these files that we include. This is basically I downloaded from internet. It's an IP block list provided by dshield.org, and it's just a list of IP addresses, right? And you can include as many lists as possible as long as you run this block !! command command in the end, all will be compressed and deduplicated into a single tree and matched efficiently, right? And then finally, I told you about this, the binary verification we use. By default, we use SHA-512, but you can use the 5 other algorithms if this is too long for you. Here's the Nginx process and all the libraries, libcrypto, libpcre, and OpenSSL, and so on, right? So this is the setup. So now I will go back to my laptop and show you the attack picture. We have here a very basic vulnerable binary that is also living on the server right now, and it's just very simple. It has a getS, and everyone knows getS is vulnerable to buffer overflows, right? But this is also a descriptive example, because from the perspective of SID, Nginx, or another process does make no difference, right? And here is the ROP chain that I wrote. It's very basic. It will execute the execve system call after fulfilling the arguments, and I can run this. And all of this is in Git. You can also try yourself. And this is how it's exploited. It will create a pound file if sorry. It will create this file by running a ROP chain. So now I'm going to try to do the same thing, but over HTTPS, and I will send this payload to the server. And I will show you step by step how SID prevents these, and I will unlock the layers one by one, and you will see how it works. So let's start with the first one. We got a permission denied, right? Let's see why. Let's go here. All right. You see the last error, right? It says not pi. It's not a position-independent executable that we are trying to execute. And the binary we are trying to execute is this one, the ROP binary, right? And because it's not pi, SID refuses to execute it. Now, what I'm going to do is I will try, if this works. Okay, it's working. Here you can see I connected to the sandbox through the IPC socket, and I will now allow pi binaries on the fly with this command. And it acknowledged there is no error. So let's try again. The same attack. It get another permission denied. Let's see why this time. So this time it's because the file is not in the force mapping. It doesn't have a checksum, right? So let's edit that one too. I saved this checksum somewhere here. You can also do this without restarting Nginx. Again, you can do it like this. Yes, so it's again acknowledged. Now let's try the attack again. Now we got a 6sys. This is different, right? 6sys is a signal that seccomp sends when the action is killed. And this 6sys is unlike the normal 6sys, cannot be ignored by the process. And this time SID will not log anything because except for the core dump, because this happens in kernel space. And if you look at the kernel audit logs, actually we can see this. And this is a bit cryptic, but you can see syscall is 59, and that stands for execve, right? All right. So let's undo this one as well. We cannot set this through the IPC socket because it's a runtime setting. You will see it returns busy. We have to restart the sandbox for this, and I will do it right here. I have all this ready. Unsafe exec is how you do it. Let's restart the sandbox. All right. So Nginx is working again. Let's try the attack again. Now and only now, after 4 tries, we get the buffer overflow, which is 6segv, a segmentation fault. And this is what your attacker is working for, right? But as I told you earlier, we have crash throttling. So let's try to do it over and over again, which your attacker typically wants to do because they want to leak memory layout from the process by crashing it repeatedly, right? Okay, I wrote it. Sorry, forgot in here. 1, 2, 3, 4, 5. Yes, it's denied again. Let's see what happened on the side. And in the very end, you see max crash is 5x seeded, and the process has been suspended from execution for the next 10 minutes, I think. If I'm not mistaken, we have the same defaults with hardened BSD. So, and only when you disable SecVGuard, you have an actually exploitable vulnerability in your hands. So there are 4 layers before you even get to exploiting the vulnerability, right? Now I will display the same thing, but this time I will do it with a SIG return-oriented programming. It's pretty much similar, just there is an extra layer which I want to show. All right, so I will go to the next directory now. Here it's the very same thing, except this is going to do a SIG return-oriented programming, which is a more portable method of doing return-oriented programming. And again, the idea is similar. When I send this, it will create a file, and we can do the same over the network. Sorry, just a second. Yes, let me change this to srop and srop. Yes, and we have seen this before. This is denied again for similar reasons. And now you learned about PI restrictions, you learned about execution restrictions, right? And let's start and try again. Now we got a SIG kill. We haven't got this before, right? SIG kill is how Sandbox kills processes when they have to be killed. And this cannot be SIG sys, because if SID sends a SIG sys system call, the process can ignore it, unlike SIG kill, right? And let's look at the logs again. And here in the very last line, you see check srop. SID actually recognized that the SIG return system call was artificial and terminated the process, right? And once, I'm sorry, let's disable this too. All right, all right. And you see, we will get the same for this. Let's just be complete and show it. So I set unsafe SIG return, so this mitigation is again disabled now. And if I attack again, you're going to see a SIG sys, which again happens because of the execv system call was passed a null argument. And once you disable this and SecVGuard, now you have an exploitable vulnerability. This is how things work. Yeah, this is all I have to show. Thank you very much for watching. Now I can take questions.
Hello. The question would be, how can eBPF and similar tools track this information? And is there a way to use already existing eBPF tools and rules to track executions and detect them?
You can do this. Basically, SID doesn't use eBPF, but this doesn't mean you cannot use it with it. You can use eBPF as an extra layer to Sandbox as well. This works. You can also use SC Linux, for example. There is no problem. SID is just an unprivileged program, so it makes it very easy to use with other tools. So eBPF would be just fine too. I never tried to do these mitigations with eBPF. I don't know whether they are possible or not, but it should be possible. We are doing CBPF, right, with seccomp. This is the classic one. eBPF is much more extended, so it should be possible. Yeah, thank you.
Any more questions? No, I think that would be all. Can we get a round of applause for Arlie?